Hi class, welcome to today's lecture on chapter 12, questions, specifically the odds questions. I need to tell you that today we're going to begin a little bit differently. Instead of starting off by just going over all the questions, I actually have to start with a continuation of the chapter 12 lecture notes, right? What I'm referring to is the chapter 12 lecture notes continued. This continued set of lecture notes is just one page, but it is a bunch of information that I do need to give to you to close out the lecture notes. So just kind of explain what's going on here. Remember that in this chapter, we are now talking about solving for an ANOVA, right? And we said that an ANOVA is an analysis of variance. It's one of those four-step hypothesis tests where now instead of comparing two group means to each other, you're basically comparing at least three group means to each other. Okay, so that was this set of notes that we went over beginning last Wednesday, right? So I explained how in the analysis of variance, you're comparing three different conditions that you can subject participants to. And basically what you're doing is you're looking to see, did these three conditions or treatments influence my participants any differently from each other, right? For example, was one of these punishments more effective than the group of punishments? Okay, so explain how to do this analysis as a hypothesis test, right? So in these notes, we talked about how there's the step one where you're forming your hypothesis. In that lecture from last week, I explained the logic of the hypothesis right here. But then I moved on to talk about steps 2, right, where you try to find your critical value, and 3, where you do your calculations. Remember that I noted that these two steps kind of get wrapped up together now with the ANOVA, where you're doing your calculations, and at the same time, you're also finding different degrees of freedom values that will lead to your critical value. From there, once you've done all your calculations, right, then we said, right, oh, here's the continuation of the calculations. Remember we were saying that now instead of solving for T, you're solving for F. The one thing that we said was when you get to your step 4, it's still a matter of you making a decision. Now you're asking yourself, is this F value that you've just calculated greater than the critical value that I found earlier? And we use the same logic. If the F value is greater than the critical value, then you will decide to reject the null hypothesis that there is a significant difference, at least amongst one of the groups. Okay, so what we were talking about was if you do reject the null hypothesis, you do find that there is a significant difference between one of the groups, then what you got to do is some further analysis, right? And this is going back to stuff that we would do even with the t-test. You have found a significant effect. Remember that whenever you did this, like say using the t-test, you would then have to follow that up by going and measuring the effect size, right? How big was the difference between one group's mean and the other group's mean? Remember, there were a couple of ways that we said that you could measure effect size. One was to calculate Cohen's d. We're not going to do that here. But another way that you could do it was to calculate r squared, which we defined as the percent of variance accounted for by the treatment, right? So the percent of that difference between the two means that you can say is due to the treatment and no other reason. Remember that when we've talked about this value in the past, we've noted that you're going to get some decimal value, and you're going to move the decimal value over two places so that you can end up changing it into a percent. You're still going to do the same thing here. Okay, when you go to do your calculation of r² with an ANOVA, though, there are a couple of things that change. For instance, one thing that changes is you're no longer referring to r² as r². Now you're referring to r² with that symbol. What is that symbol? That symbol begins with yet another Greek letter from the Greek alphabet. This one can be found over here in our alphabet, or our Greek alphabet. And the letter that we're now saying that we're going to use is this letter here, a lowercase eta. And we're saying that the way that we talk about this is now our r² is eta squared. So how do we go about finding out what eta squared is? The way that we do it is we take our value that we found as our sum of squares between, and we divide it by our value for our sum of squares total. I'm showing that I've already found what those two values are. We did that last week in our lecture notes, right? And the way that we did it was we did all our calculations. Remember that once we got our calculations completed, we wrote them all the solutions, right? All the answers in this table to help us organize all those answers. And when we did this, we got these two values, right? We got what our sum of squares between was and our sum of squares total was. We said our sum of squares between was 30 and our sum of squares total was 46. So that's where I'm getting this 30 and this 46. When we go to solve this equation, it's a division problem. So it ends up giving us a quotient of 0.65. Remember what I was saying up here is we take that decimal value, we move the decimal point over two places and turn it into a percent. So here now we're saying that 65% of the variance, 65% of that difference between the means was accounted for by the treatment. Okay, so now we're still talking about having found a significant effect with our ANOVA. Right here we're saying, okay, yeah, you found that your ANOVA value was significant, your F value was significant. Here we figured out by how much, by what percent. But remember, another thing that we're doing in the ANOVA is we're comparing at least 3 different means to each other. Right, let's go back to the experiment that we did with this. Remember that the data for this looked like this, right? We had exposed 3 different groups of participants to 3 different treatments. This group, let's kind of know, all 3 groups were driving a car, right? All the participants in the groups were driving cars. And what was being looked at as far as like a dependent variable was driving performance, right? So that's what each one of these scores is here. Each individual participants in each group's driving performance. What you're seeing amongst the 3 different groups is the group who had the no phone condition or the no phone treatment, they got the highest driving performance scores of any of the groups. Right, that kind of makes sense. Here, this group did not have a phone to distract them, so they did well on the driving performance test. Here, this group did have a phone to distract them, and it was a handheld phone, right? So because they got distracted by the handheld phone, their driving performance scores were pretty low. Same thing for group 3. They too got a phone. It wasn't as bad a situation as this phone because they had a hands-free phone, but still the researchers found that it distracted them. This group also got low driving performance scores in addition to this group. Right, so the whole point of our experiment that we conducted here was we had this group getting a mean score of 4, this group getting a mean score of 1, and this group getting a mean score of 1. In the experiment, the question that we were asking with our ANOVA was, were any of these 3 means significantly different from each other? Right, just kind of like eyeballing the 3 different means. What we should see just by eyeballing the data is that these 2 groups did not do significantly different from each other, but this group did do significantly different from the other 2 groups. Okay, at this point, right, when we're talking about measuring effect size and all this other kind of stuff, that's now where we need to go to figure out if this conclusion is true. Right, our F score, it's a weird F, our F score said that yes, there was a difference among these 3 different groups. Remember, the F did not tell us where that significant difference was. Here I'm just kind of eyeballing, kind of guessing this group is significantly different from these 2 different groups, but I don't know that just from F. In order to truly know that this group is significantly different from these 2 different groups, I have to do another analysis. And that other analysis is what's referred to as a post hoc test. What is a post hoc test? Basically, post hoc is Latin. And what does it mean? I think I may have already explained this earlier in the semester. The word post in Latin means after. And the word hoc in Latin means to this. In particular, hoc means like to this solution. All right, so what this term really means is it's going back to this idea of in this solution, we found that F was telling us that there was a significant difference among the groups. We want to know which other groups were significantly different, and that this test is going to help us figure that out. How's it going to do it? First, let's note that we would use it under 2 conditions. Right, the first condition that we would use a post hoc test under is when we've conducted an ANOVA and we've rejected the null hypothesis, right? If we've rejected the null hypothesis, we're saying that, yeah, there's at least 1 mean difference that's significant. The other conditions that you would use a post hoc test for are when you ran your test and you rejected your null hypothesis, in that test, you had at least 3 treatments or 3 conditions in the experiment. Okay, so from here, what we can note is that there are 2 types of post hoc tests that you need to be aware of. We'll say the first of these tests is this one here. It's called Tukey's Honestly Significant Difference Test, or the HSD test. Okay, so remember, we're using this to figure out where is the significant difference among the 3 different groups. We think that this group is significantly different from these other 2 groups. We're going to use this test to see if that's true. How are we going to do it? We're going to calculate HSD and use it to compare treatment means. Right? When we compare these treatment means, we're going to compare that mean to that mean to that mean, and so on and so forth. Right? We're going to see, given each difference between each mean, what is it compared to the score that we're going to get here? Okay, so the way it works is first we need to find a HSD score. How do we do that? We do it by using this formula. Right? HSD equals this letter Q times the square root of MSW divided by N. Okay, so how do we solve this equation? First, let's just note that the big thing that we need to do is figure out what is Q. What number is Q going to be? How do we figure that out? The way that we figured out is first we need to note that we need to get a hold of a Q table, right? That's going back to these different kinds of distribution tables that we've been using to find critical values. As it turns out, there's a Q table. Looks like this. I'll call it the QHSD table. And we're going to use this to find a value for Q. How do we find the value for Q in this table? We look for two coordinates again. What are the two coordinates? One is how many groups were there in the experiment, and then also how many degrees of freedom are there for your error term. Okay, so first off, remember that there were 3 groups in the experiment, and the degrees of freedom for our error term, by the way, that is your degrees of freedom within, right? We figured out what that was. We wrote this value down on a table before. We said that our degrees of freedom within is 12. And so that's how I'm getting this 12 here. Okay, so I've got my 2 coordinates that I'm going to look up on my Q table. 12 and 3. 3 is the number of groups, and 12 is my degrees of freedom. Notice that at 12, I can look for my critical value using either 0.05 alpha level or 0.01 alpha level. Ours was a 0.05, so we're going to say that our Q then that we're going to use is 3.77. Okay, so we have just found our Q. I'm not even going to call it critical value. I'm just going to call it. We've just found our Q value, right? And that says 3.77. Okay, so that's going to be, this number here is going to be the number that we're going to use for Q in our equation. We also need to know what our other 2 numbers are that we're going to have to use as part of our equation. We already figured out what our MSW was, right? Remember the way that we did that was after we'd done all our sum of squares equations, we then used those sum of squares values to figure out some mean squares values. What's being looked for in this equation are MSW, right? Our mean squares within. And that is this value here, mean squares within. That was the equation that we used to get it. Those are the 2 numbers that we got for it. Our mean squares within value ended up being 1.33. The other thing that we're going to need is the n. Notice I'm using the lowercase n here. Right, so that's the number of people that you had in each of your groups. One thing you might want to note is that if you are going to use a HSD test to figure out which groups were significantly different from each other, all the groups in your experiment had to have the same n. In our case, we're okay. That was what happened. All of our groups had an n of 5. Okay, so we figured out how to get the values for that equation. We're now going to go ahead and solve that equation. It ends up being 3.77 times the square root of 1.33 divided by 5. And that ends up giving us a value of 1.94. Okay, so now what are we going to do with that 1.94? Remember, the whole idea is we're comparing the 3 different means to each other, and so we're subtracting 2 means from each other at a time. And we're asking, anytime we make that subtraction, is the difference between the 2 groups greater or less than that 1.94. If there is a difference that's greater than 1.94, then we're saying there is a significant difference between those two different groups. However, if you take another pair of the groups in the experiment and you compare them and what their differences are, and their two differences are smaller than the 1.94, then you would conclude that there was no significant difference between these two treatments. Okay, so that's how the Tukey's honestly significant difference test works. We should note that there is a second way to calculate a post hoc test. You also could use what's referred to as a Chaffee test. Why would a researcher want to use a Chaffee test instead of a Tukey test? The reason why is because the Chaffee test is an extremely cautious test, right? Here we're saying that one where you would have the smallest risk of type 1 error. Basically, remember, a type 1 error was where you reject the null hypothesis, but you do it incorrectly, right? You rejected the null. You said that there was a significant effect when there actually was not one. This test gives you a small chance that you'll make that mistake. And it uses the same critical value for your overall ANOVA, right? So we ran our experiment using the ANOVA. We found a critical value, and over that critical value we got at the end of the experiment, and that was this 3.89. Okay, so how does one use a Chaffee test? First, I'll note that there are basically four things that you have to do when calculating Chaffee. First thing that you're going to do is you're going to have looked at your data, and you're going to decide to compare two groups to each other. And the two groups you're going to compare to each other are the two that look like they were the ones that were significantly different from each other. All right, so in this example, we're comparing these two different treatments to each other. When you go to do that, you need to calculate first, right, your first step is that you need to calculate a new sum of squares between. The reason why I'm saying that you need to calculate a new sum of squares between is because you have to calculate a sum of squares between score for just the two groups that you're looking at. Okay, so before, when we had calculated sum of squares between, and then we noted it as 30, that was when we had all three groups that we're looking at. Right, so now we're going to calculate a new sum of squares between. And the way that we're going to do it is basically use the same formula that we used to calculate sum of squares between before. Actually, what we're going to do is we're going to use the sum of squares formula, this one here. Right, so, but we're just going to use it for the two groups that we're comparing to each other. The way it's going to work is the formula is the sum of t squared divided by n minus g squared divided by n. So what does that mean in terms of actual application? It means that we're going to take t, right? Remember, t was your sum of x for each group, right? So t for group 1 was 20, and that was all the x values for group 1 added up. You're also going to figure what your t for group 2 was, right? So that's this score of 5. Once you've got each of those t's, right? So your t for group 1 and your t for group 2, what you're going to do with each of those t's, you're just going to square them. So I'm squaring that one here, and I'm going to square that one here. Each one is going to go over their respective n. Right, and then you also have to figure out g squared. in this case, remember G was the total of your T's. When it was the 3 groups, you had a G of 30 because that was what the 3 groups T's added up to. Now you're going to get a new G, and it's going to be just the sum of the 2 groups that you're comparing, right? This group's T and that group's T added up is going to give you this new G. So what do we end up with? We end up with 20 squared over 5, and that's at 20 over this 5, plus 5 squared over 5, that's that 5 over that 5, minus 25 over 10. Where am I getting that 25 from? That's that T plus that T. Where am I getting that 10 from? That's that N plus that N. That gives me this big fraction problem. Ends up giving me a sum of squares between value of 22.5. Okay, so all of this was your step 1 of your Chaffee test. Once you've got that part knocked out, then you can move on to your step 2 of your Chaffee test, which is to figure out what your critical value is. Remember we said here that you're going to use the same critical value as you did for your overall ANOVA, right? So if that's the case, the critical value, the degrees of freedom that we had was 2 over 12, and that gave us this critical value of 3.89, right? So that's your second thing that you've done for the Chaffee. That leads you to then the third thing that you have to do. Now you have to calculate a mean squares between for the 2 groups that you're comparing. Right, the way I'm going to do that is I'm going to say, okay, it is going to be my sum of squares between divided by my degrees of freedom between. Here I'm saying that my sum of squares between is 22.5. Where am I getting that from? Remember I got that 22.5 when I calculated all this here. That gave me this sum of squares between. So I got 22.5 as my sum of squares between, and that's over my degrees of freedom between, which is 2. And so that gives me 11.25. From there, I'm then going to say, okay, so that's what my mean squares between value is. That leads me to the fourth thing that I have to do. The fourth thing you have to do is now calculate F using the information that I've been given, right? So remember, my F value is now solved by calculating mean squares between divided by mean squares within. I've just set my mean squares between was 11.25. I'm going to use my original mean squares within value, which was, right, mean squares within was 1.33. So I end up with an F value of 8.46. Remember, the whole thing that you're doing now is you're asking, is that 8.46 greater than my critical value of 3.89? It is. So my fourth step that I'm going to do is that I'm going to go ahead and say I'm going to reject my null hypothesis and conclude that yes, there is a significant difference between these 2 treatments. Okay, so that's everything I needed to say in finishing off your Chapter 12 lecture notes. From there, we'll go ahead now and get into the Chapter 12 odds props. Okay, and then to do this, I'm just going to tape this down real fast and go over the questions the way that we've been going over them so far this semester. Right, so we've got a question 1 here, and it says, explain why the F ratio is expected to be near 1 when the null hypothesis is true. This question is referring to in our chapter 12 lecture notes, where we talked about the logic of the F test, right? So this is the answer right here inside the notes. But just to recap what I said here, we can say that the big point that we made was that we said, okay, the new value that we're calculating is F. How do we get F? We said that F is made up of this thing called the between treatments variance divided by the within treatments variance, right? BTV was between treatments variance. WTV was within treatments variance. We said that each of these types of variances had different components within them, right? And so now I want to point out what those different components were. We said that the between treatments variance was made up of two types of variance. We said it was made up of systematic variance and unsystematic variance. What were those two different kinds of variance? Remember, systematic was where you were comparing each group to other groups, and you were asking, is this group's mean different from that group's mean? Right? And it's systematic variance in that the reason why the means would have been different from each other is because this group was treated differently than that group was, right? For instance, that might have been the group that got the timeout punishment. That might have been the group that got the chancla punishment, right? We're asking, did the punishments have a different effect? Remember, there was also that third group, right? The third group was that group who got shocked. Okay, so that's what systematic variance was all about. Is there a difference between the groups? We also said that this numerator made up another kind of variance though too, right? So in addition to this systematic variance, it also consisted of this unsystematic variance. What was that unsystematic variance? Remember, that was the variance that was present within a group, right? So for each one of these groups, we took each individual's raw score and subtracted that raw score from the average of the group. And if there was a difference between this and this, that was referred to as unsystematic variance. Why was it unsystematic? Right, because it was not part of the system that the researcher imposed. Everybody within a group was treated exactly the same, so there was no reason for them to be different that was due to what the researcher did. Let's just note that the denominator of this fraction, right, the within treatments variance, also consisted of this unsystematic variance, right? So it also was that kind of variance. So the idea here, right, why would your F be 1 if the null is true? The reason why is because remember that null is saying that there is no difference between this group, and this group. If there is no difference between the different groups, then them being subtracted from each other is going to equal 0. Right? We said that whereas this value was 0, we're always going to have some unsystematic variance, and that's going to be at least 1. That same unsystematic variance would be here in the denominator as well, right? So then if you do have this situation where the null is true, the way it's going to be true, and the way it's going to equal 1 is you're going to have a fraction that's going to be 1 here over a 1 there, right? And that's how you end up with a 1 as your F value. Okay, so I'm going to go ahead and move on to question number 2 from there. Right? Question number 2 is asking, describe the similarities between an F ratio and a T statistic. Let's just remember that this lecture is only focused on the odds questions. And you're supposed to do the evens questions on your own. I'm going to go ahead and give you the answer to this one, though, just because I don't think that I answered this question in lecture. Okay, so what's the question again? Describe the similarities between an F ratio and a T statistic. Just this question, let's just remember that one way that the two are similar is that you are using both statistics in the same way. With both statistics, you're using that four-step hypothesis testing procedure. The only difference between the two is that you're using this one if you have two groups, using this one if you have more than two groups. Okay, how else are they similar though? What else is really important? So I just explained here how the F value is made up of this ratio of between variance over within variance, right? We said the between variance consisted of both the systematic and unsystematic variance, and the within variance just consisted of the unsystematic variance. As it turns out, that T equation is exactly the same. It too is looking at between variance compared to within variance. The way this is doing it though is that equation where it was the two groups minus each other, right? That's what was happening here. But then the way that they're capturing this within variance was that standard error. Okay, so that's the answer to number 2. Go ahead and move on to question 3 from there. It says, why should you use ANOVA instead of several t-tests to evaluate mean differences when an experiment consists of 3 or more treatment conditions? This is another thing I didn't really talk about in the lecture notes. So I'm just going to give you a sense of what the question is asking. Right, it's kind of going back to a situation like this where you had 3 different treatments present in your experiment. Basically what the question is asking is, why didn't you just run a t-test repeatedly? Right? Why didn't you just run a t-test where you compared those 2 groups to each other, and then a t-test where you compared those 2 groups to each other, and then another t-test where you compared those 2 groups to each other? Right? Why didn't you just do these several t-tests? The answer to that question is this. When you do a lot of t-tests, right? When you do, I should use this word repeated. Let's use the word that you had here, several. When you do several t-tests on like one set of data, the problem that occurs is that the chance of type 1 error increases. What was that type 1 error? Remember, that was falsely rejecting the null hypothesis, right? So rejecting the null hypothesis when you're not supposed to. More specifically, a type 1 error is where you say that there's a significant effect when there actually is not one, right? So doing repeated or doing several t-tests increase the chance that you're going to make that kind of mistake. Okay, so let's go ahead and move on to question number 4 then. Question number 4 is asking for you to calculate these 3 different values: sum of squares total, sum of squares between, and sum of squares within for this set of data. Let's just remember that we went over how to do this in your chapter 12 lecture notes. And the place that you go refer to in your notes is the page 2 of the notes. Here's your formula for that sum of squares total. Here's your formula for your sum of squares within. And here is your formula for that sum of squares between. Okay, so I'm just going to leave that part at that. Go ahead and move on to question number 5 from here. And say that the question for 5 is, a researcher uses an ANOVA to compare 3 treatment conditions with a sample of n equals 8 in each treatment. For this analysis, they want you to find the different degrees of freedom, total, between, and within. Let's just remember that We talked about where to find those. Going back to your chapter 12 lecture notes, remember those were also in that same spot where you can find your sum of squares formulas. Okay, so what is my degrees of freedom total? First, let's just remember that to find this, the formula is uppercase n minus 1, right? So it's the n in all of the groups that you had in your experiment minus 1. We had 3 groups of 8, so that gave us a capital N of 24. Minus 1 gives us degrees of freedom total of 23. Next, degrees of freedom between can be gotten by subtracting 1 from K, where K was the number of treatments that you had. Here we're saying that there were 3 treatments, so your equation becomes 3 minus 1, which gives you a degrees of freedom score of 2. Then the last one, degrees of freedom within, that's at uppercase n minus your lowercase k, right? So your 24 minus your 3 gives you a degrees of freedom within of 21. Okay, so that's everything that you need to do on question number 5. For question number 6, again, this is going to be something you're going to do on your own. Let's just kind of read it real quick. It says researcher reports an F ratio with degrees of freedom between of 2 and degrees of freedom within of 30 for independent measures ANOVA. How many treatment conditions were compared in the experiment? Basically, what you're supposed to be able to do is use this information to get at the number of treatment conditions, right? What was K in this example? Then once you figure that out, you should be able to use that to figure out, well, how many participants were there in the study, right? Think this logic there for answering this question. So we'll go ahead and move on to question number 7 from there. 7's asking, a researcher reports an F ratio with degrees of freedom of 2 and 27 from an independent measures research study. Remember that how for the ANOVA, how that degrees of freedom works, right? So you're supposed to go look up some critical value on an ANOVA F table using these 2 coordinates. Where am I getting those 2 coordinates? Remember, that is your degrees of freedom between and your degrees of freedom within, right? That's what those 2 numbers are. Different set of data here, but that's where they would show up on your summary table. Okay, so for this experiment, they have 2 questions. First question is, how many treatment conditions were compared in the study? The way I figured that out was they said, okay, I've got my 2 degrees of freedom here. That 2 is my degrees of freedom between. And the way I got it was I subtracted I subtracted 1 from K, right? Degrees of freedom between. So if my degrees of freedom between is 2, what that must mean is that my formula was 3 minus 1. So there were 3 treatments. Okay, so now moving on to question B, they're asking, what was the total number of participants in the study? Here, I'm using my other degrees of freedom value, that degrees of freedom within, which was 27. Remember, the formula for this is capital N minus K, right? Capital N minus K. We just saw that K was 3, so this is n minus 3, and if n minus 3 is 27, that must mean that there were 30 participants in this study, right? Because that would be 30 minus 3 equals 27. Okay, so let's go ahead and move on to question 8 from there. All right, so this is another evens numbered question that you're supposed to do. Just take a quick look at it before we move away from it. Looks like it's basically asking the same kind of question as you saw in question 7, so I'm going to leave it alone. Go ahead and move on to question number 9. here the question is saying, the following values are from an independent measures study comparing 3 treatment conditions, right? So you had a treatment condition here, treatment condition there, treatment condition there. What they want you to do is first compute the variance for each sample, right? So variance for each sample, that's where you're supposed to calculate S squared. How do we get it? Remember, it's the sum of squares divided by the degrees of freedom. They basically give you those two values, right? For instance, in group 1, they told you that the sum of squares value was 63. And they also indirectly told you that degrees of freedom was 9 by telling you n was 10. So then that gave you a sample variance of 7. For group 2, it's 66 over 9. Gives you 7.33. And then for group 3, it's 87 over 9, which gives you 9.67. From there, you're supposed to use those 3 values to now compute your mean squares within, which would be the denominator of F ratio for de novo. Okay, so how do we go about calculating mean squares within? The way that I did it was I went back and I remembered, how did I get mean squares within? Remember, it was a fraction of sum of squares within divided by degrees of freedom within. What do we remember this? Right, this is page 3 of your chapter 3 lecture notes, and there's the formula right there. Okay, so in our case, what I did was to get sum of squares within, I added up the 3 different sum of squares value. And that gave me a total of 216. I also figured out degrees of freedom within, right? Remember, degrees of freedom within is where you take your total number of participants and you subtract the number of treatments. Right, so I got 27. The way I got 27 was my total N was 30. I subtracted 3 from the 30, right, because I had 3 treatments, and they gave me a degrees of freedom within value of 27. That, in turn, made my MSW value 8, right, because 8 is the quotient of 216 divided by 27. Now, before I leave this question, I do want to leave off with a point they're making at the end of question B. Right, so we've just computed our mean squares within value, said it's 8. They're saying this additional note. Because the samples are all the same size, you should find that your MS within, right, this value here, is equal to the average of the 3 sample variances, right? So this is equal to the average of this, this, and this. I'd like to just ask you guys to average those 3 values out and see if they do equal that value. Tell me if that's correct or not. In the meantime, I'm going to go ahead and move on to the next question. Next question is 10. And here they've got a fill-in-the-blank problem for you, right? So they have a problem here, and they've created a F summary table, right? Remember the F summary table was the same kind of table that we created here on our page 3 of our lecture notes. They partially filled it in, and then they give you a couple of hints in here. They say a researcher conducts an experiment comparing 4 treatment conditions with a separate, right, I think that's going to be important, 4 treatment conditions with a separate sample of n equals 6 in each treatment. An ANOVA is used to evaluate the data. And the results of the ANOVA are presented in the following table. Complete all missing values in the table. And they have this hint to start with. Begin with the values in the degrees of freedom column. Right, so try to use this information to fill in this information. And then once you have that, you should be able to use it to fill in the other blanks. Okay, from there, Before I let you guys go, I do want to ask you to complete one full ANOVA. So I'm going to kind of give you one full ANOVA problem as an example problem. And then after we're done going over this together, I'm going to give you another one for you to do on your own. But what we'll do right now is we'll just kind of go over the different steps that we follow to get the ANOVA. So here we're saying that in this question is, the following data were obtained from an independent measures research study comparing 3 treatment conditions. Use an ANOVA with an alpha value of 0.05 to determine whether there are any significant mean differences among the treatments. Right, so you got treatment 1, treatment 2, and a treatment 3. Basically what we're going to do is we're going to follow all of the steps, particularly these steps and these steps, to see if our null hypothesis is true or alternative hypothesis is true, right? To see if that's true or if that is true. Okay, first thing we had to do was for each group, we had to get a series of values. I'll go over each group one at a time. Okay, so this is the series of values that I had to get for group 1. First thing I needed to calculate was their T. Remember, for the ANOVA, the T is the sum of all the raw values for that group. Right? So I added all those raw values up and ended up getting 16 for these. Next thing I got was for that sample, how many participants were in there? There were 8 participants. And so then I calculated the average raw score value for the group. The average value was 2. From there, I needed to figure out what was sum of squares for this group. Right, so I used my sum of squares formula, the computational formula. First, I figured that my sum of x squared was this 48. Then I had to figure out what t squared was, so that ended up being this 256, right? So that's that 16 times 16 gives the 256 over n, which is that n right there. And so that's how I got the sum of squares equals 48 minus 32. 32 is this right here, equals 16. So for this group, the sum of squares value is 16. So then I had to do the same thing for the other 2 groups. Group 2's sum, right, of their values was 24. They had 8 participants. Their mean score was 3. Their sum of squares value was 24. So then I did the same thing for the third group. Their raw scored sum was 32. They had 8 participants. Average raw score was 4. Their sum of squares value was 20. Okay, once I had all those preliminary values, then I was able to use them to do the next set of value gathering. Right, then I also had to figure out what was the sum of x squared. Remember the way that we did that was we took all of the x's and we squared them, and then we added them all up, right? So each x value got squared, and then all those squares got added up, and they ended up being that 292. From there, I needed to figure out what G was. Remember, G is the total of all the T's. It ended up being 72. Then I had to figure out how many participants I had in all 3 different groups. Each one had 8. So there were a total of 24 participants in the experiment. Number K is the number of conditions or treatments. There were 3 different conditions, 3 different treatments. So K equals 3. Now I can use all those values to start to figure out sum of squares and degrees of freedom information. First sum of squares values that I calculated were sum of squares total. Remember the way that we got that was with that version of the sum of squares equation. Here it ended up being 292, right, that value there, minus 5,184. The 5,184, I believe, was that value squared over the 24, which was my capital N. That ends up giving me a sum of squares total value of 76. I also had to calculate my degrees of freedom total before I moved on. Remember, this was capital N minus 1, so it gives me a degrees of freedom total of 23. The next sum of squares value that I had to calculate was sum of squares within. Remember, all sum of squares within is where you add each individual sum of square value, right? So 16 plus 24 plus 20 gave me a sum of squares within value of 60. Also need to calculate degrees of freedom within, and remember the formula for that was capital N minus K. So capital N minus K gave me degrees of freedom within value of 21. From there, I went and calculated sum of squares between and also degrees of freedom between. Remember the way that you calculate sum of squares between is this time it is the difference between your sum of squares total and your sum of squares within. Right, so I figured that my sum of squares total was 76 and my sum of squares within was 60, so it became 76 minus 60 gives me 16. Then my degrees of freedom between, the formula for that was K minus 1, so 3 minus 1 gave me 2. Remember, the next step from there is to then go calculate my mean squares. The first mean square value that I'm going to calculate is mean squares between. Here I'm saying that it's 16 over 2. How is it 16 over 2? The way that it's 16 over 2, so mean squares between is your sum of squares between over your degrees of freedom between. Sum of squares between divided by my degrees of freedom between gives me a value of 8. Same thing with mean squares within. That's my sum of squares within over my degrees of freedom within. That is 60 over 21, gives me 2.86. From there, remember the next thing I have to do is go calculate F. What makes F F? Remember that F is a division problem. Your mean squares between divided by your mean squares within. In this case, it was 8 divided by 2.86, gave me an F value of 2.79. Remember, this is the point where I go and I look at my degrees of freedom to get my critical value. Notice that my degrees of freedom were 2 and 21, right? So I got my F table, my 2 column, and my 21 row gives me 3.47. And that's what I got here, 3.47. So now, right, I'm at that step 4 of the ANOVA. I'm comparing the F that I calculated to my critical value F. Here I'm seeing that the F that I calculated is smaller than my critical value F. So I have to conclude that I have to accept the null hypothesis, right? So that is the result of my ANOVA analysis. My ANOVA analysis is telling me that there is no significant difference between the means of the 3 groups that we analyzed, right? None of these 3 means are significantly different from each other based on the results of this ANOVA. Okay, so that's everything on how to calculate the ANOVA. I'm just going to leave you with then this last problem where you'll go and calculate the ANOVA on your own. Thank you very much.